Welcome to a new episode of the ITU Journal webinar series, where you can find insights and forward-looking research on future and evolving technologies. The ITU Journal is an international journal providing complete coverage of all communications and networking paradigms, free of charge for both readers and authors. This publication considers yet-to-be-published papers addressing fundamental and applied research, building bridges between disciplines, connecting theory with application, and stimulating international dialogue. Its interdisciplinary approach reflects ITU's comprehensive field of interest and explores the convergence of ICT with other disciplines. We count on your support to make this webinar an interesting experience. Please submit your questions via the Q&A channel at the bottom of your screen. All questions from the audience will be taken during the Q&A session after the talk. The meeting is being recorded and the recording will be made available on the webinar website. Closed captioning is also available for this event. You can enable this by clicking on the closed caption icon at the bottom of your screen. We hope that you will enjoy the talk and we encourage you to stay connected until the end for the Wisdom Corner. I will now give the floor to our Master of Ceremonies.
Hello, and welcome to the new webinar series with academics of the IT Journal on Future and Evolving Technologies. My name is Alessia Magliarditi from ITU, the International Telecommunication Union, the United Nations Specialized Agency for Information and Communication Technologies. It is my pleasure to open our fourth webinar of this season with Dr. Elsa Erkip from New York University. Please submit your question via the Q&A channel. We will address them to our speaker during the Q&A session. And after the Q&A session, as just announced by our avatar, I will moderate the Wisdom Corner, live life lessons. So please stay online. Dr. Erkip agreed to a personal chat. She will share with us some lessons learned over the years that might perhaps be useful for some of you. I'm very pleased to introduce Professor Ian Akilditz, Editor-in-Chief of the ITU Journal and founder and president of Truva. Professor Akilditz is Ken Bayer Chair Professor in Telecommunications Emeritus at the Georgia Institute of Technology. Professor Akilditz has established many research centers worldwide, including in South Africa, in Spain, Saudi Arabia, and Finland. He's Editor-in-Chief Emeritus of Impact Factor journals, highly cited and at the top of the most prestigious international rankings. Ian is visiting distinguished professor in several universities around the world. Among his current research interests, there are 6G wireless systems, terahertz communication, metaverse, communication in challenged environments. So Ian, the floor is yours for your opening remarks and to introduce our speaker and moderate the Q&A session. Thank you.
Thank you, Alessia. Distinguished guests, esteemed colleagues, and honored participants, good morning, good afternoon, and good evening, wherever you are joining us from across the globe. A warm welcome from Abu Dhabi to our distinguished international audience. It is both an honor and privilege to inaugurate Season 4, Episode 4 of the ITU Journal on Future and Evolving Technologies, in short form ITU JFET webinar series. This season continues to set new benchmarks, bringing together an unparalleled assembly of thought leaders. Today, we are exceptionally honored to introduce one of the leaders in our research field, Professor Elsa Erkip. Before we proceed, let us take a moment to reflect on the vision and transformative impact of our journal. Launched in December 2020, our journal was founded with a bold mission to bridge academia and industry, accelerate innovation, and foster global collaboration at the cutting edge of research. As an open access journal, we are deeply committed to democratizing knowledge, ensuring that groundbreaking research is freely accessible to all, with no cost to readers or authors. Every submission undergoes rigorous peer review, upholding the highest standards of academic excellence while emphasizing real-world applicability and timely innovation. The journal's remarkable success is a testament to the dedication of an extraordinary team. I extend my deepest gratitude to Sizo Ono-san, Bilal Jamoussi, Alessia Magliarditi, Erika Campilongo, Maria Otero, and countless others whose tireless efforts have shaped ITU Journal into the premier platform it is today. We invite you to researchers, innovators, and industry leaders to contribute your pioneering work to our journal. If you have ideas for special issues on emerging technologies, we welcome your proposals. Now it is my great honor to introduce today's distinguished speaker, one of the leading researchers in information theory and coding for wireless communication systems, Professor Elza Erkip, who is an institute professor in the Electrical and Computer Engineering Department at New York University, Tandon School of Engineering. Elza holds a BS in Electrical and Electronics Engineering from Middle East Technical University, Ankara, Turkey, MS and PhD degrees in Electrical Engineering from Stanford University in the US. Her pioneering research spans information theory, communication theory, and wireless communications. A fellow of the IEEE and a member of the Science Academy of Turkey, Professor Erkip has been recognized with numerous prestigious awards, including the NSF Career Award back in 2001, the IEEE Communication Society WICE Outstanding Achievement Award in 2016, IEEE Communication Society CTTC Technical Achievement Award 2018, and also IEEE Communication Society Edmund Howard Armstrong Achievement Award in 2021, and Information Theory Society's Padavani Lecturer Distinction 2022. Her seminal contributions have earned her multiple Best Paper Awards, including IEEE Communication Society Stephen O. Rice Paper Prize in 2004, and IEEE Communication Society Award for Advances in Communications in 2013, and IEEE Communication Society Best Tutorial Paper Award 2019. Beyond her research, Professor Erkip has held key leadership roles, including President of the IEEE Information Theory Society 2018, member of the IEEE Information Theory Society Board of Governors from 2012 until 2020, and distinguished lecturer of the IEEE Information Theory Society between 2013 and 2014. And she also served as an editor-in-chief of the IEEE Journal on Select Areas in Information Theory, as well as served as the chair of IEEE Communication Society Communication Theory Technical Committee. I first had the privilege of meeting Professor Erkip in 1998, a long time ago. She still looks young though. During her visit to Georgia Tech, over the years, I have witnessed her meteoric rise as a leading authority in her field, contributing seminal research that has shaped wireless communications over the past 25 years. With an exceptional Google Scholar H index of 57 and over 31,000 citations, her work continues to drive transformative advancements in the field. Without further ado, please join me in giving a warm welcome to Professor Elza Erkip. Elza, floor is yours.
Thank you so much, Ian, for the very nice introduction, and it's kind of really a pleasure to reconnect. Even though we have reconnected many times after so many years. You were kind enough to host me at Georgia Tech when I was a junior researcher. I still remember, and now I have a daughter who goes to Georgia Tech, so every time I visit her, I have the kind memories of my visit. So thank you so much.
Thank you.
Unfortunately, we have some kind of technical difficulties today, so I'm gonna have one of my colleagues share my slides for me. I think that's a testament to the need for further technological advancements. My Zoom started acting up this morning, so if we could share the slides. Thank you, and I'll kind of tell next. Sorry for the interruption for our audience. So today I want to talk about some of the recent work we've been doing in my group on learned compression, particularly for its applications towards 6G. And we're going to be doing compression for particular communication tasks at hand. So if you could go to the next slide. So a very quick background, thank you for the very, very kind introduction, Ian. So, currently I'm a member of the ECE department at NYU Tandon School of Engineering. I just celebrated my 25th year, with a very nice dinner that our provost was hosting for all the 25-year, members of the community. I'm also a member of an academic industrial, research center called NYU Wireless. We have several member companies. Our membership keeps growing, and it provides, a vital, infrastructure for our wireless research to grow and to be relevant for industry. If I could have the next slide. My own research group is called Communication and Information Theory Group at NYU. Unfortunately, this is somewhat of an old picture taken a few years ago on one of our, fine outings. But several of our research group members have gone onto industrial and academic research positions. We are mainly interested in some of the theoretical foundations and practice-oriented applications of wireless and networking. But beyond wireless, we look at problems in security and privacy, both within and outside of the wireless settings. And we have some recent work focusing on compression problems, both for compression of images as well as for wireless applications. If we could go to the next slide. So I'm just going to take you back, further back than 1998 when I first met Ian, to 1948 when Shannon wrote his seminal paper. So his goal was to understand how to communicate an information source to a remote destination. Next, please. In doing that, he broke down the problem into two components. The first one thinks about an information source that is to be compressed in the most efficient manner and sent over an ideal rate-limited channel for the destination to recover the source either losslessly or within a distortion measure. So this way, Shannon was able to understand, what are the best strategies for, compressing an information source. Next. The next problem he isolated was, what if, we imagined an ideal information source, simply a sequence of bits. How would we transmit these sequence of bits over a noisy and distorted communication channel? So this was his communication problem, where he established the notion of capacity and how to get close to the capacity of a communication channel. Next. And of course, he studied how to put these two aspects together, how to do, separate versus joint source channel coding, meaning, first compress the source, then communicate over the channel, conditions under which the separation becomes optimal, which of course has kind of led to development of these two fields in tandem, as well as joint source channel coding when it would be advantageous to take into account both the source and the channel in designing optimal strategies. Next. Now, this field has made a comeback in recent years where, we hear about how to exploit the source semantics in order to communicate more efficiently over communication channels. So with that in mind, if we could go to the next slide, I want to today talk about compression, but for the purpose of enabling wireless networking. So we're not going to have an explicit communication source, information source in mind. Next. But we will be looking at how enabling task-aware compression can improve wireless networking. And we will identify in this talk two scenarios in which compression of signals in the network could lead to more efficient communication. So instead of in our compression schemes, instead of minimizing distortion, as we usually do with compression schemes such as image compression, video compression, our goal would be to optimize the task at hand, and the task would be defined by the network operation, as I'll elaborate next. So in particular, we're gonna postulate that learning, with the sophisticated machine learning tools we have at hand today, allows a flexible, adaptable, and efficient task-aware compression, particularly suited for our wireless network. Next. So the talk today is going to talk about two particular examples of this, and it's some of the recent work that we've been doing in my group in the past couple of years. And both will involve a task-aware co-design of compressor and decoder, again, for the purpose of improving wireless networking. The first problem will be about channel state information, or CSI feedback. So in any kind of in modern downlink cellular communications, base stations are typically equipped with very large numbers of antennas, and in order to maximize downlink throughput, the base station carries out precoding so it can serve multiple users at the same time using its antennas. Now, in this problem, having accurate channel state information at the base station is very important so that the base station can do proper precoding to minimize inter-user interference. Now, more recently, the issue of obtaining, the concern of obtaining accurate channel state information has been of even particular interest because of the increase in number of antennas and the complexity of sending that channel state information, uplink towards the base station. And in particular, this channel state information typically needs to be quantized because it has, a very large dimension. And one of the TGPP study items is looking at how this channel state information feedback can be efficiently carried out using AI ML tools. And this is, where the work that I'm going to describe, fits in. And I'll kind of elaborate a little more on that as we go through the talk. Next. The second, application that we're going to look at is relay networks, which are making a comeback, through the use of non-terrestrial networks, cooperation of base stations in various forms, intelligent reflective surfaces. And in this context, we're going to look at how compressing and forwarding correlated received signals by network terminals can lead to higher throughput. Some of the theoretical foundations have been established, a while back, but practical applications have been limited, and we're going to see how data-driven approaches can actually facilitate such strategies. Next, please. So I want to acknowledge, my collaborators in this work, particularly Fabrizio Carpi, who is a recent graduate of my PhD group, has led the work in both domains. For the second piece of work that I'm going to talk about, relay networks, Ezgi and Fabrizio contributed, equally in establishing some of the foundations. And my NYU colleague, Siddharth Garg, has also been part of the team, as well as, Bell Labs collaborators, where the first line of work was started when Fabrizio did his internship in Bell Labs. So next, please. So let's talk a little bit about, the first problem, channel state feedback in multi-antenna systems. So we're going to envision a frequency division duplex system, meaning the base station needs to obtain accurate channel state information, accurate downlink channel state information through sending pilots to mobiles, which are then fed back in a separate feedback link back to the base station. So the way kind of this typically works in today's systems is that the base station sends pilots to downlink users, orthogonal pilots to downlink users. Next, please. Then these users, each of the mobiles, will estimate their downlink channel. And then in order to send it back to the base station, they compress their channel state information because this is typically a very high dimensional system. And the uplink resources for sending channel state information is somewhat limited. Next, please. So then this compressed channel state information is sent over limited rate feedback links to the base station. Next, please. Which is then used at the base station to do a reconstruction of the channel state information, which then determines the proper downlink precoding. So it is very important to have accurate channel state information so that the downlink precoding scheme is as accurate as possible in order to minimize inter-user interference. Next, please. Then actual information or data is sent in the downlink using the precoding vectors that the base station designed based on the channel state information that it has received. Next, please. So overall, this scheme, has been very, influential in increasing downlink data rates. And as you can see, the proper compression of channel state information and proper design of the corresponding downlink precoding vectors are essential in getting the throughput benefits of this system. So conventional channel state information compression, follows, more conventional compression strategies such as vector quantization and compressed sensing. Next. More recently, with the emergence of deep learning in pretty much all the technological and non-technological fields in the world, there has been an interest in applying deep learning-based compression schemes to channel state information compression. So it has been shown that deep learning-based compression outperforms conventional methods and comes with fewer assumptions. Next. Now, most of this literature attempts to compress the channel state information for the base station to reconstruct the CSI, and then the base station can use, traditionally used precoding vectors such as, zero forcing, match filter, and so on and so forth, based on this, estimate of the channel that has been reconstructed. Next. However, if we are to step back and think about this problem, for a little bit, we kind of see that the ultimate metric of compression, the ultimate success of compression, is not dictated by how well the CSI reconstruction at the base station is. Rather, the ultimate metric is spectral efficiency. When the base station uses this finite feedback obtained from the compressed CSI of each of the mobiles, and then uses them in some precoding and sends information downlink, the ultimate measure of success would be how much can we increase the throughput? So this leads us to thinking about task-oriented CSI compression. Next, please. So in this context, we're going to be looking at precoding-oriented task-aware CSI compression. So the task would be for the base station to design its precoding vectors in order to maximize achievable downlink rate. And the constraint is the limited feedback overhead. So that's what makes the compression scheme task-oriented. Next, please. Now, the picture that I showed you earlier was about a single cell. But of course, we live in a world with multiple cells where there could be intercell interference among the users. So we're going to be thinking of how to design the CSI feedback in a multi-cell downlink setting. So just to illustrate it, suppose we have an array of base stations serving a number of users. And because of the proximity of some of the users to neighboring base stations, there is intercell interference. Next, please. So, how would a kind of pilot transmission, CSI feedback and downlink transmission work in that case? So each base station, in the channel estimation phase will transmit its pilots towards the mobiles. Next, please. So as you can see, as the base station is sending its pilots, these pilots will be received not only in the users belonging to that base station cell, but also in the interfering cell's mobile users as well. Next, please. So, as you can see, this could, go on. So now each mobile user is going to receive a separate pilot, one from its serving base station and others, from the base stations that cause interference at that mobile. Next. So then in forming CSI compression and sending this compressed CSI back to its base station, each mobile can now send bits not only about the channel towards its serving base station, but also towards the interfering base station as well. That's what's denoted in these kind of red feedback bits. Now, what we envision is for each base station to send these red feedback bits. So if these red feedback bits, to the kind of interfering base stations, so that each base station can design its precoding vectors, not only thinking about the users in its own cell, but also thinking about the users that it's interfering with. Now, of course, if the base stations are able to share, bits over the backhaul, they could also share user information and the actual data bits as well. But in this setting, we're not considering such information sharing, which would increase the demand on the backhaul. We are simply, thinking about sharing the compressed CSI bits over the backhaul so that each base station can design its precoding vectors to minimize interference. So this would, limit the constraints on the backhaul as compared with a full base station cooperation setting. So next, please. So the system model we have in mind is a base station M with the following downlink signal. Next, please. So this downlink signal it contains the precoders, which are denoted by the red vector V, that precode all the users that base station is serving. Now, remember, the Vs are going to be designed not only with the users in that particular cell, but also with the interfering users in mind as well. So when we look at this from the perspective of a particular user, the received signal at user K in a particular cell will consist of several terms. The first term is the desired information that's coming to that user. The second term is the intra-cell interference. This is the interference that the user experiences because there are other users in the same cell. And kind of even with a well-designed precoder, each user will receive some leakage from information going to the users within the same cell. And the third term is the intercell interference. This is signal coming from neighboring base stations that are interfering with that user. Next, please. So then, overall, the signal to interference plus noise ratio of a particular user is going to be the ratio of the received power of the desired user to the received power, the total received power of intracell interference plus intercell interference plus noise. So next, please. And then when we look at the network sum rate, each of the rates for the users will be a function of their SINR. So we can model them as log 1 plus SINR. And we can think about the total network sum rate as the sum over all users in the network belonging to all of the M base stations. So our goal would be to maximize this rate. So effectively, we will be interested in minimizing or maximizing the SINR by properly adjusting for the signal power received, desired signal power received at users, as well as intra and intercell interference. Next, please. If focusing on a particular user, in this case, user K in cell M, essentially in the pilot or channel estimation phase, the user will receive pilots from its desired cell. So that's the link that's in the bottom part of user MK, as well as it's going to receive pilots from the interfering base station. Remember, we kind of schematically, we only had a linear array of base stations. So here, just for illustration purposes, we're assuming that a user receives interference, only one-sided interference from one of the base stations. Next, please. Then the user processes these pilots, obtains the channel state information, and sends the channel state compressed channel state information feedback in the uplink. The black arrow coming out of this user goes to its serving base station, and the blue arrow coming out of this user through its serving base station and through the backhaul goes to the interfering base station. And then each base station can use all of these feedbacks to design their downlink precoders. Next, please. So the kind of what I'm going to illustrate is how to design the pilots, the compressor at the base station. So every block that you see in yellow highlighted is going to be a block that is designed using neural networks. So starting with the pilots at the base stations, continuing with the compression schemes at each user, as well as precoding strategies at the base station. And the way we're going to design these compressors is by borrowing results from neural image compression to do efficient compression. And we're going to see that indeed some of the features that were originally developed for compressing images more efficiently are very useful in CSI compression as well. So next, please. So I'm going to step back for a second and tell you a little bit about how this neural image compressor works. And then we'll come back to our wireless CSI compression setting and discuss how it can be used in a wireless network. Now, the classical image compression scheme is JPEG, right? This is one that we're very familiar with. And the way JPEG works, the kind of the main blocks in JPEG is that the signal or the image is first transformed using a linear transformation, typically DCT, and then kind of into a kind of sparser space. And then these transform coefficients in this transform domain are quantized, digitized and quantized. And so next, please. So the encoder f sub theta maps the signal into a transform domain, and this encoder is linear. Next. Then followed by quantization, we use entropy coding. So entropy coding essentially looks at these quantized transform coefficients and tries to squeeze out the remaining redundancy. So it's typically an optimal lossless compressor, such as Huffman coding or arithmetic coding, which have very efficient representations. And then and then at the decompressor, we get these quantized transform coefficients and pass them through a linear decoder, which is the DCT inverse. So next slide, please. Now, when we move into the neural compression, image compression domain, which was initiated by a 2017 paper of one of my collaborators and now one of my colleagues at NYU, Yona Bellet. The idea was the following. So let's kind of keep, next please, let's keep the general block diagram of JPEG intact, but now instead of applying a linear transformation, we think of the transformation at the encoder f sub theta as designed by a neural network. So the encoder can be nonlinear, and this was termed as nonlinear transform coding, in order to kind of further exploit, the features that can be extracted from that image. Next. So this learned nonlinear transform coding is again followed by quantization of transform coefficients, followed by entropy coding. Next, please. In fact, if we can go to next. Yes, here. No, if we could go back. Thank you. Yeah, sorry, I made you move too fast. Yes. One more. Yes, very good. Oh, it's okay. It's okay. I wanted to, go back one, but that's fine. So kind of, what I'd like to highlight is that in this learned image compressor, one of the powerful things that a neural network can do is learn the transformation at the encoder, as well as the corresponding transformation at the decoder, but also learn, the accurate probabilistic model of the quantized transform coefficients so that entropy coding can be done properly. Now, as we're going to see, when we come back to CSI compression, learning the proper probabilistic model to do good entropy coding is important in further compressing these quantized transform coefficients, which will also be important in CSI feedback. Okay. So now taking this kind of neural image compression framework, which by the way has been very successful, and now JPEG has a feature called JPEG AI. So the learned image compressor is surpassing the JPEG standard in a variety of metrics. So now taking it back to our communication problem, we're going to think of CSI feedback and compressing CSI using the architecture that has been very influential in image compression, so Bellet architecture. So, when we're using this compressor, again, we're going to have our channel state information estimate at the user. So what I'm showing you on the left-hand side is what the user does, is a nonlinear transformation at the user, followed by quantization and entropy coding. And we're going to discuss, which of these parameters are learned. And then at the base station, first it will be entropy decoding, followed by a neural network-based module that does precoding. Next, please. So during training, the blocks that we need to learn are the nonlinear transformation, which will lead to efficient compression at the user. The entropy model, with which we will do entropy coding at the user, as well as the module at the base station that designs the precoding vectors. So next, please. So I think we were at slide 17. Thank you. Yes, one more, please. Okay. So again, during training, we'll use pseudo quantized features to learn the probability model. Next. And then in order to measure the compression rate, we will use, the entropy of the pseudo-quantized features as measured by this cross entropy term. Next, please. So in order to learn, what's being done at the base station precoder as well as at the user, compressor, we need to define proper loss functions. Okay, so our loss function incorporates the feedback overhead, right? Because, we have a finite rate limited feedback link to send our CSI, compressed CSI, as well as the performance. So the feedback overhead is measured by entropy rate of our pseudo quantized features, and the performance is measured by the network sum rate achieved with the designed precoding vectors. Next, please. So mathematically, we can write them as follows. One thing I would like to point out is that in the second line, O sub M sub K, we see the feedback rate or the feedback overhead coming from the compressed CSI for the desired base station, as well as the compressed CSI for the interfering base stations. So we take both into account, and in fact, in our results, we're going to see the various trade-offs in feeding back the desired compressed CSI and the interfering compressed CSI. And the performance is based on the total rate achieved in the network. So next, please. So, let me show you, some of our kind of results and how well this neural network-based CSI compression scheme works. So we'll look at a multipath channel, a base station with uniform linear array, 64 antennas, 8 pilots, and we're going to control the intercell interference by a parameter alpha. Next. So we'll look at various scenarios to understand how the learned CSI compression scheme works. First, we'll have single cell, multiple users. So this will only incorporate intracell interference. Then we'll extend it to multi-cell, multi-user. So we'll also see the impact of intercell interference and how the limited feedback bits are divided between the intended and the interfering base station, and then we'll study some robustness issues. Next, please. So a quick kind of comparison with the literature, and you'll see it in our performance comparisons as well, of kind of mainly focusing on different learned CSI compression strategies. So some of the kind of literature includes, task-oriented compression and precoding, but the feedback is not optimized. By optimizing feedback, I mean the use of entropy coding, which, as we will see, is an important component. And some of the literature uses feedback optimized, but is more towards reconstructing the channel. So next, please. So the first result I'm going to show you, has the overhead or feedback rate in the horizontal axis and the, achievable communication rate in the vertical axis. And we're going to look at a very simple scenario, 1 cell, 2 users. The blue line is the performance we would get if the base station had perfect channel state information and was using zero forcing precoding. And the red line is perfect CSI at the base station, maximum ratio transmission. Next. The next set of curves, tell us the performance of one of the kind of results in the literature if the CSI compression was based on reconstruction of the CSI rather than being task aware. We see that as the feedback rate improves, the CSI compression performs well. Next, please. The black curve is the one that is precoding oriented. So the goal here is not to reconstruct the CSI, but to maximize the downlink rate. As you can see, the performance is better when the feedback rate is smaller. But because the feedback is not optimized as the feedback rate increases, the performance falls below the reconstruction oriented setting. Next, please. The green curve is what we have proposed, which kind of exploits the benefits of both. It is both precoding oriented and feedback optimized, and gives the best performance and catches up to perfect perfect CSIT zero forcing case pretty quickly. Next, please. So now we're going to look at 2 cells and 2 users. So we're only going to look at, the learning strategy that we have developed, because we've seen in the previous slide that it surpasses other strategies. So again, I have the total network sum rate in the vertical axis and the average total feedback rate per user in the horizontal axis. The top black line is, if we had uncompressed feedback and no intercell interference, and the blue line is if we had uncompressed feedback. Again, we're looking at learned strategies, but full interference. So the interference power is as strong as the power that's received for the desired users. Next, please. So when we have look at the no interference case with learned and compressed feedback, we see that it catches up with the ideal uncompressed feedback pretty quickly. Next, please. Now, as we increase the interference level, of course, the performance goes lower. But still kind of improves with increasing feedback. And one thing I'd like to point out is that the numbers that you see over each point is the ratio of the feedback that's allocated to the desired base station's feedback, to the serving base station's feedback. So as the feedback rate is increased, we see that ratio gets smaller, meaning the mobile starts allocating some of its feedback to the interfering base station CSI for that interfering base station to mitigate its intercell interference. Next, please. Now, as interference increases, of course, the performance gets worse, but the trend is the same. And more feedback bits are allocated to the interfering base station. Next, please. And the trend continues. Next. So next, we look at some of the robustness issues. What would happen if we had 1 cell, 2 users? So we go back to the single cell case. where we trained, we're testing this at 0 dB SNR, but we trained at a different SNR, okay? So now we see that if we learn at 0 dB, test at 0 dB, we have the green performance. Next, please. As the train SNR gets further away from 0 dB, the performance gets worse as expected because we have a mismatch scenario. Next, please. But now if we train the compressor at the user at a different SNR, right, and freeze it because, it's harder for mobiles, to adapt, but have the base station adapt to the test SNR. We see that, in these dash curves, we regain most of the benefits of learned compression and get very close, especially as the feedback rate increases, to a match setting where the test and train SNRs are the same. Next, please. And in fact, if we were to learn, not with fixed SNR, learn the compressor, but learn it at a range of SNRs, we don't even have to fine tune the base station precoder, and we will get kind of most of the benefits. Next, please. So to summarize, in this first, portion of the talk, we talked about precoding-oriented learned CSI compression, where we borrowed ideas from learned image compression for useful feedback optimization. Next, we were able to trade off between feedback overhead and system performance in multi-cell, multi-user MIMO systems. Next, please. We've seen that fine-tuned base station provides robustness by compensating for the use of mismatched user models. Alternatively, we can train over a range of SNRs. Next, please. Now I want to, devote a little bit of time to the second problem that we're going to investigate in looking at how compression, in-network compression, can be useful for wireless networking. And we're going to be looking at relay networks. Next. So relaying and multi-hop in 6G networks is becoming a reality. And those of you who've been around, as long as maybe me and Ian, have seen a kind of that this relaying and multi-hopping literature making a comeback. What's old is new again. And I'll kind of give you a quick recap of what happened decades ago. But essentially, relays can improve throughput and coverage in a variety of settings and can be used in a variety of settings, such as cooperation of base stations, non-terrestrial networks where multi-hopping is essential in reaching high altitude, reflective intelligence surfaces, and so on and so forth. Next. But one of the building blocks in these kind of multi-hop networks is the relay channel. Next. Which was introduced, several decades ago. It's a very interesting problem in multi-user information theory. Many groups worked on it. Capacity for the general relay channel is unknown, but several relaying strategies have been proposed. And today, we're going to particularly focus on compress and forward, which makes minimal assumptions at the relay and enables it to forward signals in an efficient manner, but requires efficient compression of the relay signal and forwarding. So I'll describe how compress and forward works very shortly. Next, please. So the building block of any multi-hub or cooperative network is the three-terminal relay channel, where a source wishes to communicate with a destination with the help of a relay. So the goal of the destination to understand the information that the source sent. Relay's sole purpose is to kind of process the signal that it has received YR and generate a signal to transmit towards the destination XR, which is received at the destination as YDR, which then the destination can put together with its own observation of the source to increase, throughput, reliability, and so on and so forth. Next. One of the important kind of sub classes of relay channels is what's called primitive or out-of-band relaying, which essentially says that the relay and destination communicate through an out-of-band link of limited rate R. So this could be a backhaul link. This could be a link in a different frequency band. So it is kind of in some sense simplifies the relaying problem. On the other hand, it is a very reasonable assumption to make in practice. So we're going to be focusing on this, out-of-band relaying in today's talk. Next. Now, the thing to kind of realize in this relay channel is that what the destination and the relay receive are, of course, correlated. They both depend on the same source signal. So the question is how we can exploit this correlation in designing the relay transmission towards the destination. Next. So we're gonna, so it has been recognized, and this is the strategy that we're gonna exploit today, is that, if the relay could exploit this correlation with the destination signal and utilize distributed compression strategies, such as the ones known in the literature as the Wiener-Ziv compression, then the relay could efficiently compress its own signal at the compression rate R and send to the destination. Okay. So this compression needs to take into account, to be the most efficient compression, needs to take into account the destination signal that the relay cannot see, yet somehow it is correlated with the relay signal. And it is known that compress and forward is optimal in certain settings. Next. However, there have been, very few practical distributed compressors, especially ones that you can, put out in the field and be robust to various modeling assumptions. Next. So in today's talk in designing neural compress and forward schemes, we're going to leverage some of the work that we've been doing in my group with my PhD student Ezgi and my collaborator Yona Ballet, on learned Wiener-Ziv compressors and adapt them to a wireless network. So next, please. So I'm going to give you a very quick overview of what these kind of learned distributed compressors do. So maybe stepping back, what do I mean by distributed compression? So imagine, and this could be any compression problem, imagine an encoder that wants to compress a source X for a decoder to receive a possibly distorted version X hat within distortion D. But the decoder has some correlated side information. Now, beyond compress and forward, this could be two camera images that are distributed in space. They're looking at the same scene, and hence they're correlated. Now, the encoder cannot see what the decoder is seeing, but knows or maybe can learn in a data-driven fashion the correlated pattern. Next. So what we did kind of in our learned Wiener-Ziv compression framework is that we the red blocks, the encoder, decoder, and the entropy model was learned using machine learning tools in a data-driven fashion to give us, good performance. Next. So I'm just gonna quickly, show you this slide. It's not kind of maybe easy to understand on a first glance, but what our distributed Wiener-Ziv compressor was able to do is to kind of recover some of the information theoretically, optimal encoder and decoder behavior. And it was kind of an interpretable way to learn this encoder and decoder. Maybe to quickly highlight, on the vertical axis, we show quantization, learned quantization kind of regions for our encoder. and same color represents the same compression index. Normally, you would assign a different index to different quantization regions for the decoder to be able to recover. But in this case, because the decoder has some side information, we were able to reuse the same index in distinct quantization regions, which is known as binning in the information theory literature, and which is shown to be optimal in theoretical asymptotic settings. So our learned distributed compressor was able to kind of recover some of that behavior. So next, now we're gonna kind of think about this setting for compress and forward. Next, please. So we're gonna be learning the relay encoder, which is the green box, and the destination demodulator. Now the goal is not to reconstruct relay signal at the destination, but to help the destination decode its information, which we're gonna call W. So next, please. One of the reasons why we looked at this primitive relay channel is that it is known that compress and forward is optimal for, for a very simple relay that is known to be oblivious, and having an out-of-band link, makes compression easier. Next. So we're going to be interested in task-aware compression. Again, the task is symbol detection or demodulation at the destination. So the goal is to minimize probability of error at the destination or maximize the communication rate, subject to a rate constraint, compression rate constraint by the relay. Next. So how do we do learned, compress, and forward? So at the relay, similar to the framework that we've seen earlier for learned image compression and for distributed compression, at the relay, we're going to have a neural network learn the encoder, the transformation of the relay signal, as well as the entropy model to do good entropy encoding. And at the destination, we're going to learn how the destination can optimally demodulate using neural networks. Next. And as a baseline, we'll compare with a simpler compression strategy where the relay does not use side information to compress. So that would be a much simpler way to compress. So we'll design the relay compressor without taking into account the destination side information. Next. But then we're going to allow it to fine-tune the demodulator, using the destination signal. Okay. Next. One more, please. Okay. So our goal, again, we need to define a loss function. Our goal could be to maximize the communication rate or the minimize probability of error at the destination. Next. So our loss function takes into account the compression rate as well as the two goals of minimizing error rate or maximizing communication rate. And those, or both of those, could be formulated using this categorical cross entropy. So that's the second term in our loss function. The first term is a proxy for the compression rate. That's another cross entropy term that measures the rate of the compressor. Okay, next. So I want to show you some results. So we've tried, simple channels, simple modulation schemes, one-dimensional as in PAM or two-dimensional as in QAM, and I'll kind of illustrate some of the results. If we could go to the next slide. Okay, so here on the horizontal axis, I'm showing the relay rate. And in the vertical axis, I'm showing the communication rate that's achieved. Of course, when the relay rate is 0, it's as if we don't have a relay, so it's the direct source to destination. And the dashed line is if the relay and destination had infinite rate among themselves. So this would be similar to a multi-antenna destination. So that would be the horizontal line. The solid line is the theoretically optimal compress and forward rate. Now let's see how our neural relay performs next. So if it uses BPSK, it is able to achieve the green dashed line is the multi-antenna receiver using BPSK. So with kind of reasonable number of bits, the learned relay is able to compress, getting close to the perfect relay to destination channel rate. Next, as we increase the modulation level, the performance gets higher and it approaches its kind of ideal relay destination channel case. Next, and the trend goes on. So next slide, please. Now I want to show you how the symbol error rate kind of performs. The previous one was throughput. This one is the error probability, symbol error probabilities as a function of the relay rate. The bottom solid line is perfect relay, multi-antenna destination. So we see that the orange curve, which is kind of the neural relay, slowly catches up with the perfect relay. The pink line is our benchmark, which is the point-to-point compression that is then fine-tuned, which is not able to perform as well as distributed compression. Next, we also show the impact of separately, so this was a 16 QAM, separately compressing the in-phase and quadrature components, which kind of leads to a simpler compression scheme, but doesn't perform as well. Next, and we also have kind of the brown curve is a more sophisticated distributed compressor, which we call the conditional, which gives the best symbol error rate performance. Next. I also want to show you some robustness results. As in the case of CSI compression, what if we designed our scheme, at a particular, relay and destination SNRs, but trained at one SNR, but tested at a different SNR. So as you can see, kind of when you train at a particular SNR and but test somewhere else, the model performs well when your test SNR is in the vicinity of your train SNR, but the performance kind of deteriorates as we get further. Next, one could of course look at the kind of best, the matched and compare with that. Next, and interestingly, training on a range of SNRs gives performance that is very close to the matched one. So this is a strategy that's been known to work in a variety of scenarios, not only in our setting, but training in order for robust performance. Training on a range of SNRs is a good idea. So next one, I'm almost done. I have a few slides. So kind of one of the things that we were really excited, even though this is a simple setting, it shows us the benefits of using learning to do kind of this compression in a relay network. But one of the things that really kind of excited us was that we could interpret the results and see, how some of the information theoretically optimal strategies showed up in learning as well. So to illustrate this, I'm going to show you a simple 4-PAM modulation. So imagine, the source sends one of these 4 symbols across a triangle, a star, or a square. And in the horizontal axis, I'm showing you the relay, the destination signal. In the vertical axis, the relay signal that's been received. Next. Now, if the relay had 2 bits of compression, right, it would probably do some kind of hard demodulation, figure out its its estimate of the transmitted symbol and send it to the destination, right? So kind of the quantization boundaries that I'm illustrating here are the ones learned by a neural network, which follow the optimal quantization boundaries if the relay had 2 bits. But in this setting, the relay only has 1 bit. So what should it do? Next. We see that the relay learns to kind of take these 2 bits and reduce them to 1 bit by reusing the same quantization index. So in this case, the same color means the same bit sent to the destination. So the relay learns to group the triangle and square regions, if you will, together, which we call binning or grouping, because they're further apart, but it still will help the destination because the destination has its own observation. Okay, so these are all learned and they follow, what you would kind of expect a scheme like this to do. Next. And furthermore, when we look at the demodulation at the destination, without the relay signal, the destination demodulator would put the decision boundaries in the middle of the modulated symbols. But now we see the following. Let's focus on the blue region. If the destination gets the blue index from the relay, it knows that either the cross or the star are more likely than the triangle or the rectangle. So it kind of correspondingly enlarges the decision regions for the cross and the star. So this leads to a better demodulator and better performance at the destination. Okay, so we were very excited to see this binning and optimal demodulation strategy emerging from learning. Next. So kind of, I don't think we need to go through this, but you can see similar behavior in a 2-dimensional constellation as well. Next, where the relay learns to best allocate its 1 bit onto kind of 4 modulation symbols, and the destination's demodulator, if the destination gets the blue color from the relay, knows to enlarge the regions, the demodulation regions, decision regions for star and triangle. Next, and similarly for the red index as well. Next. Okay, next. I think we can kind of, so to quickly summarize, we can use some of the learned distributed compression framework, which we developed for source coding or distributed compression in a communication network to design neural network-based, compression forward strategies. These strategies are in fact quite simple. Once you learn them, it becomes a lookup table and can be made to be robust. Next, please. So in this talk, I kind of presented 2 examples of task-aware compression based on learning by neural networks for wireless networking. One was kind of maybe closer to practice because it's a 3GPP study item, precoding-oriented CSI feedback. The other one is detection-oriented compression forward relays. Next. And in both cases, it was important to design the compressor in a task-aware fashion with appropriate loss functions of neural networks with the domain kind of inspired knowledge. Next, of course, this is just the tip of the iceberg. These are kind of very simple examples that I'm kind of showing you, yet provide pathways toward interpretable neural network-based compression, further issues for investigation, robustness. Next, scalability when dimensions increase, whether it's users, cells, or relays, things can get complicated to train and to deploy, yet it's kind of worthwhile investigation. Next, and practical channel and network settings. Next, as well as as neural network structures and architectures kind of change at a very fast pace, one could provide further improvements on both the choice of neural network architecture and training methodology. Next, here are kind of links to a few of the papers that I mentioned here. And with that, I think I'll stop. So thank you so much.
Thank you, Elsa. Very nice. And I asked the audience to ask your questions in that Q&A box. We already have one question, but to give more time for the audience, I can start with some general questions, and then I will try to get hopefully more questions from the audience. So Elsa, the question is about how does your approach compare to semantic communication, where the goal is also to transmit information relevant to a task rather than raw data?
Yeah, I mean, I think these are all kind of, I always like to joke that we need a semantic for semantic communication, right? Because the semantics could mean a number of things, right? So it could be that you actually have an information source, right? And instead of humans, machines are going to look at it, right? So there, the semantic could be a particular thing you want to do with that information source. Or the semantic could mean a particular task, as in the case of the CSI compression, the task is to maximize the downlink rate. So I think it is kind of, I see all of these as one big field, right? Task-aware, semantic communications. There are different, different researchers and different kind of people use it in different, specifics. But I see this in this kind of one big class. Exactly.
True. And also, from the machine learning optimization perspective, since the compression is learned end to end, how do you ensure robustness against distribution shifts, for example, changes in channel conditions or network topology?
Yeah, perfect. I mean, it's a very, very valid concern. I think what I showed was some initial studies we did, right? So we said, the simplest change in channel conditions is the SNR, right? So you wanna be able to deploy these compressors, and you don't want a different compressor every time the user moves, right? Or has a different SNR. Or maybe, there could be a few kind of things that the user can change. So that's why we were looking at changing SNRs. So if you train over a range of SNRs, and then, use it on a particular SNR, there seems to be some robustness. I mean, this is known. We're not the first ones looking at settings like this. Of course, you could look at more complex settings. For example, as the users come and go, right? This is going to be especially at the base station. The pre-coding is done based on the received CSI feedback of all the users. If you're reconstructing your channel, you know how to do pre-coding. This is something we know, right? You could do zero. Now, if you're doing task aware, then you need to take into account the number of users, the quality of the CSI feedback from all users. These are all very, very valid kind of
concerns.
Issues, concerns to look at, as well as ease of implementation. But I think and again, there are many people looking at, including 3GPP, looking at neural network-based CSI compression. But we think kind of these studies are pointing in the right direction, to do more analysis.
Okay, thank you. There is a question from Satish Kumar. He says, what do you mean by backhaul-based exchange of the CSI feedback to neighboring stations?
Okay, good question. So we're envisioning the following, right? So so base stations are connected through backhaul, right? Now, so you could kind of completely ignore that backhaul connection in doing downlink transmission, right? In precoding, which is what you would get in a single cell. But then when there's cell interference from neighboring cells, that will show up as interference, and the precoding cannot kind of fight against that, right? What we're proposing here is that what if through the backhaul each base station, would exchange some of the CSI feedback. Particularly in downlink pilot transmissions, the user would estimate the CSI coming from the interfering base station, compress it, and allocate some of its feedback bits to this, interfering base station CSI. Then the interfering base station could use that feedback bits. It's only a small portion, as we've seen in the curves, could use these feedback bits to design a precoder to try to avoid this interstall interference. And kind of that, seems to work better than ignoring the feedback. And we think that the amount of feedback needed in backhaul link would not be that extensive because it's only sharing a portion of the feedback bits and not actual information. But of course, in practice, we would have to see, right, where this lands.
Thank you. And there's also a question from York Earwaker. Actually, he has 3 questions or sub-questions. So the first one is, how much of the ANN learning compression will be live on the wire to learn real-world communication? And another sub-question is, how does the ANN compression and decompression impact latency? That's always a concern, right?
Of course, yes,
Then
yes.
how will network providers likely use this for throttling?
Yeah.
Kind of like congestion control, I assume, right?
Yeah. So kind of what I showed here, right? Again, these are very initial results, was you train offline, right? You deploy, and then, again, it was a very simple robustness analysis, but in that setting, you train offline, you deploy, and then you use it, right? Of course, as you're running, you could update your training and, maybe adapt to the network conditions, right? So there could be a feature like that as well. So some of those implementation aspects we have not considered, but those would be valid concerns. But I would say, as a starter, right? Because the previous kind of reincarnation of CSI feedback simply uses fixed fixed feedback code books, right? So everything is fixed. Now you could again fix them, but learn them using a neural network, right? And then you could further improve your learning as you're operating the system. The second question was latency. Now, some of these kind of neural networks that we learn are not, that complex. We have not measured latency, but these aren't very complex neural networks, especially, okay, so if you're doing images, maybe you need more, right? But I think that the channel conditions, if you go to frequency selective, it may still get complex, but I think they're kind of simpler than images. And I'm not sure how complex that would be, but that's a good point. That kind of needs to be taken into account. And what was the last question about?
I think we should also continue.
Okay, sure.
We spent too much time for this question.
Okay.
I have another 2 sub-questions, actually. You talked about CSI feedback compression. This is mostly for the use case in 6G cases, right? So how does the learned scheme compare to traditional codebook-based or sparse recovery methods in terms of overhead and performance?
Yeah, so that I did not include because some of we were only comparing with the learned methods. Because I think in those papers, again, these are academic papers, right? But in those papers, they had provided some comparison, with the traditional methods, showing advantage of learning. But yeah, I did not include them here. I believe there are kind of advantages. Now, of course, these are academic papers. When you put them in practice, we'll have to see,
How they perform.
Of course.
I mean, that's the always missing part in this, the transition from the theory, from the academic work to the real world outside. But sometimes it's successful. So
Exactly,
of
exactly.
course, it's not always disjunctive, right? So there's always success. So another
And
question is,
sorry,
Elsa, from me,
yeah.
you also mentioned about neural CF relaying. I think
Yes,
you
yes,
showed some results, but
yes.
how does the system handle varying numbers of hops or dynamic network topologies?
That's also a very good question. That was like the first piece of work, we did just again, proof of concept, single relay, how does compress and forward work? We're now currently working on the multi-relay setting. You could put, multiple relays in a multi-hop fashion, or you could put them in parallel. Then the compression scheme becomes more complex because now you have these multiple relays that observe correlated versions of the transmitted source, right? So this distributed compression in its ideal setting becomes more complex. But that's something we're working on. In fact, my students were kind of sending me plots and diagrams yesterday. That's certainly a worthwhile direction. Our goal was kind of to get this first setting and then see how much of this are we get as things scale, are we getting the benefits? Is this an easy implementation or does it become kind of overwhelming?
There is one question and normally we don't take questions from anonymous attendees, but he or she, I don't know who that is, asks a question about in-network computing or in-network processing. I think the person is saying be considered in the use cases, particularly on how the models are deployed and what are the challenges. It's a little bit too broad question, but anyhow, if you want to answer, because we have 2 minutes, so that Alessia can take over and ask you some more live questions,
Yes, yes. So again, I don't know, right? So what is kind of in network computing could be it's like semantics, right? Could be
Right.
anything and everything. I think in this specific case, if you're, compressing signals, then I think kind of at least these two pieces of work and others in the literature give you a sense of how that can be done.
Yeah, actually, I saw more, but anyhow, York is always here, York Earwaker. He gives you kudos, excellent presentation. I hope
Thank
the others
you.
also liked it.
Thank
And there's one more question, but I don't know, Alessia, am I allowed to ask this or you want to take over?
Yes, please, maybe with a short answer. Thank
I
Okay,
you.
hope
very
so. I
short.
don't know.
Right.
So it's good that there are questions, right? So
Yes,
the
absolutely.
person is Ahsen or AHCN, Ahsen or whatever. What is your view on the integration of goal-oriented versus task-oriented techniques with classical source coding techniques? This is again more tutorial type question.
Yeah.
And are we able to adapt them to the new paradigm, or do we need completely novel schemes that are based on DL? I mean, it's a long, anyhow.
I mean, conceptually, I think kind of similar, but of course, implementation-wise, you need to look at the task at hand. Sometimes maybe it's simple, you don't need deep learning. Sometimes it's more complex, maybe you need learning. I think it depends on the context, I would say. But it's a worthwhile direction to investigate.
Sure, of course. Good,
Yeah,
good answer.
that's a very
Thank you.
short
That's
answer.
the smart Elsa. I love that.
Thank
I
you
love
so
Years,
that part
much.
years
of
of
you.
being a professor, right?
That's I love that part of you a lot. It's very good, right to the point.
you.
So again, I thank you for the excellent
Thank you so
presentation,
much.
also
Thank
handling
you.
the
Thank you.
questions. I thank the audience. Please do not leave us, because Alessia will take over and then we'll ask some life lesson questions to Elsa. And please, Elsa and Alessia,
Thank
go ahead.
you. Thank you so
Thank
much.
you. Thank you
Thank
so
I'm
you.
much,
here.
Ian.
I'm
So,
here.
yeah, welcome to the Wisdom Corner. So, we changed that offering a unique and special angle to this series of webinars, adding a personal touch. So, I would start with my first question. Looking back on your journey, what is the most valuable life lessons or even a failure that you have encountered that shaped your path? And how can this lesson inspire or guide those attending the webinar?
Yeah, very good question, because there are many failures, right? Some small, some big. I think maybe one was kind of, so my PhD was, purely on information theory. I did not know anything about wireless, when I graduated. And it was an era where kind of wireless was booming. So this was kind of mid to late 90s. And I, quickly realized that, I wanted to be in academia. I quickly realized that, well, okay, so whatever I learned in my PhD is not immediately and directly useful. And I need to learn a new field. So I spent a few years at Rice University. That's when I visited Ian, and my primary goal was to learn about wireless communications. But, so kind of initially, of course, you do all this work in your PhD and you're like, okay, now I need to pivot in order to be employable. But I think one of the pleasant things that I realized, so that failure turned into success, that a lot of the things that I used and kind of did in my PhD regarding multiple users in an information theoretic setting, turned out to be very, very useful in wireless. So in a way, what was kind of at some point a failure then turned into a success, because I was able to leverage what I had kind of learned and studied earlier. So it's, so it's always ups and downs. I think, you get up one morning, right? Things aren't working the way, you want to. So hopefully the next day will be better, and you can kind of always be on the lookout for using your kind of background and strengths in a way that, benefits your career and gives you a productive future.
Yeah, thanks. And actually, in particular, what advice would you give to young professionals aspiring to build a career in academia or research? In your experience, what essential skills and qualities contribute most to success in these fields?
Yeah. I think, first of all, I want to acknowledge this is kind of an interesting time in research and academia. We have an exceptional number of talented, junior people, which of course makes it a little more competitive.
Yes.
But I think, to be successful in research, but maybe kind of in any field, is to, one needs to be resilient, right? There'll be failures. You send a paper, it gets rejected. It gets horrible reviews, right? It happens to everyone. And then we don't like it, right? So we all want to be successful. But it's always to kind of take it, be upset about it for an amount of time, just grieve.
Yeah.
And then step back and say, well, okay, what do I learn from this review, right? Can I improve my paper? I'm going to make this work. So some kind of robustness and is essential in being successful in research, because, it's always, you think you've got the greatest result, then you notice, a problem with your result. So one needs to be robust. That requires technical skills, but also the emotional skills to kind of tell yourself, I'm good. I'm going to make this work. Have the emotional support system as well as technical support.
Yeah, that would be essential. Yeah, absolutely. And what first inspired your passion for your field, and how did you turn that interest into an important career?
Yeah. Well, okay. So first, I have two brothers who are kind of older than me. There's a big age gap, and they're both academics.
Actually,
Oh,
I wanted to I wanted to just say that, by the way, it comes from her genetics, her family.
Oh,
Yes.
okay. That's
Yes,
interesting.
I didn't decide, my family decided. But it was also the competitiveness in me, I think, So when I started elementary school, my oldest brother started his PhD, right? So I didn't know what a PhD was, and I said, that's what I'm going to do. Why? Because he's doing it, and I need to do it too, right? So kind of competitive. But I really enjoyed kind of being in school, and I enjoyed, math and applications of math. So when I started graduate school, so initially I was working on something a little different. But then, you know, I became familiar with information theory, some of the probabilistic foundations, and it kind of really fascinated me. To this day, it continues to fascinate. And then kind of, as I mentioned earlier, you know, wireless was becoming hot when I finished my PhD. So I thought that would be a good, you know, field to move into. And I found that kind of really bringing my information theory background and understanding, you know, wireless problems and kind of making this marriage allowed me to step back and kind of think about problems in a more fundamental way. And to this day, kind of, I find it very, very useful. So I think in the end, it kind of worked out. There's always an element of luck. I think maybe an advice to researchers, but you know, maybe we create the lucky environment in the sense
I think so.
by persisting, we create you know, environments where, you know, hopefully something good will happen and we'll take advantage of it.
Wonderful. Thank you. And among your career achievements, is there one particular contribution, whether professional or personal, that has a profound impact on you or on others? And what makes this accomplishment especially meaningful for you?
Yeah. So I think one of the things that I really, really like is students, like
Oh,
working with
yeah.
students and seeing them grow. You know, so it's a long journey, right? So we get PhD students, you know, they're very good, but you know, they're learning. So it takes you know, an effort, you know, to grow with them. And I think one of my proudest moments is when I see my students kind of being successful, you know, thinking deeply, making important contributions. I think that's, you know, I mean, that's the thing that I'm kind of very, very proud of. I'm also proud of, you know, the technical work that I did. But I think the contribution to, you know, the technical course, and I feel kind of very, very close to my students, and kind of seeing them grow is the most wonderful thing.
Wonderful. Thank you so much.
Thank
Thank you so
you.
much
Thank
for
you.
sharing your lessons and your advice with us and with the audience. Thank you, Ian.
Thank you. Thank you, Elza, a lot. Thank you
Thank
very
you.
much.
Thank
Really,
you.
it was fantastic.
Thank
And I
you.
hope to see you somewhere soon.
Yes, yes, yes. Fantastic.
And
Wherever you are in the world.
yes, regards to the family. And thank you, Alessia, for again hosting this show. I call it
Thank
show.
you. Yeah, thank you very
And
much. It was a pleasure to host, actually, Dr.
yeah,
Yeah.
Rakib.
and we have
On the
another
29th,
in 2 weeks. It will be about terahertz communication.
yeah, with Professor Chong Han.
Yes. So we are also distributing worldwide. So Chang'an is from China, mainland China. And so we are having the best, you know, currently active researchers. So we are very proud of being able to attract all these people like Elza and others. So thank you again, Elza.
Thank
Have
you
a
so
nice
much
evening.
for the kind
Thank,
invitation and the wonderful event. Thank you
thank
so
you. It was a
much.
Thank
pleasure.
you.
Bye-bye.
Ciao.
Thank
Ciao.
you.
Bye-bye.
Bye.
Happy Easter, by the way.
Oh, yes. Bye.
Yeah.